Welcome to our talk at the Open Slava. My colleague and me will fill you in today in our topic, Sustainable Quantum Portfolio Optimization. But first, let us introduce ourselves.
My name is Tim Leonhardt. I'm actually very glad to be back here in Bratislava at Open Slava because 4 years ago I joined Accenture because a client asked Matthias Ziegler if we do have a quantum expert there, and I just was about to finish university, and he even invited me to Open Slava and help him with preparing the presentation. I'm very glad that after now 4 years we can talk a little bit about what we have actually implemented using this technology that I did my research on as a physicist. And now to you, Melissa.
My name is Melissa Schmidt. I am mostly in technology architecture in Accenture, and I'm working here now since over 2 years actually. And yeah, I'm actually a software developer. So it's a combination of physics and software development, I think. And you can also see our contact, so you can also send us an email or send us a message on LinkedIn. So what we present you today is our application. We call it Qupo. It's a quantum portfolio optimization. And this is just a preview that you can see here. So it's portfolio management. And we compare different algorithms from a classical base and a quantum simulated base with each other. But we talk you through each step so you can actually understand what you see here. So first, what's the use case? Our use case is sustainable portfolio management. In short, social and ecological friendly robo-advisor. So we did this project in cooperation with our client, KfW. KfW is a German state-owned sustainable it's a bank and it focuses on development. And you can also see these 17 Sustainable Development Goals here on the right. And these Sustainable Development Goals are stated by the United Nations as goals for the year 2030. And our client doesn't just support them, but also tries to make them measurable. So our business challenge here is actually not just portfolio optimization, but sustainable portfolio optimization. So we tried, as optimization already says, we try to find best solution to a problem from a set of possible options, given certain constraints. And our constraints is one side the risk factor, and on the other side sustainability factor. So we want to build a portfolio to yield the maximum possible return while maintaining a certain risk and also taking sustainable measurements in consideration. And we build our calculations on Markowitz's portfolio theory. And this goes actually back on Herr Markowitz's concept on portfolio optimization back to the year 1952. And actually, he found out that instead of focusing on the risk of each individual asset, he demonstrated that a diversified portfolio is actually quite less volatile than the total sum of each individual part. So that means that while an asset has a certain risk and it might be quite high, a portfolio that holds this asset might be quite less. Like the volatility of that portfolio might be quite less. And why did we choose this to solve also with a quantum computer is because portfolio optimization is actually known as an NP-hard problem. And this means an NP-hard problem is defined as a problem that cannot be solved by a classical computer in a certain amount of time, a certain amount of computing power. So don't get me wrong, portfolio optimization can be solved with a classical algorithm. We do solve it with a classical algorithm, but it rises in complexity very fast, and on a certain level, a classical computer cannot solve it in a certain amount of time with a certain amount of computing power. So that's why it's actually quite it fits for the quantum computer. So let's look at the data that we base our portfolio optimization on. We basically fetch all the data from Yahoo Finance API. And on the one side, we have the historic market data. So we choose the stocks that we want to include in our portfolio and then get the stock prices from the finance API. So you can see here as also an example from Adidas and Airbus. It's a random month in the year 2021, where you can see the prices of the stocks varied around like €1 basically. But this is the base of what we feed our algorithms with. And on the other side, so to make it sustainable, our solution, we took the ESG values. This is our sustainability measure. And the ESG stands for environmental, social, and governance. And it's basically a rating of companies to evaluate how sustainable they operate. So part of environmental is, for example, how do they handle climate change, or how much of carbon emissions do they produce, or how do they handle energy efficiency. Part of social is, for example, it's all about people and relationships. So how high is the customer satisfaction, or how are the labor standards. And part of governance, it's like about running a company. Is there any bribery or corruptions going on, or do they do a lot of lobbying, or are there any known whistleblowers? And so these actually are non-financial factors, but in recent years, it has actually shown that these non-financial factors are getting increasingly more important when making investment decisions. So you can see also here an example of Adidas and Airbus ESG ratings, and you can also see that Adidas has a quite better ESG rating than Airbus. Understandable, considering what they do.
Okay, now let's have a look at what's currently state of the art of quantum computing. You probably, most of you watched the presentations before, so what we present to you today is a showcase and a proof of concept on how you can use quantum computers in the cloud and other algorithms and integrate them to build a new application that gives you an idea of what you can improve when quantum computers get better, that show you what kind of skills you need, what kind of people you work together. And that was actually also the reason why we worked with KfW on the topic, because they had very similar questions to the questions everybody has when they approach quantum computing. The first question is a little bit like, so what do I actually want to improve? So what is the idea of the value prospect? Do I just want to make something more efficiently? And Ezio Armando talked about this. That's not a business case. That's kind of nice. But what I really want to have is something really new, that's completely different. That kind of tends my needs in a way that it wasn't possible before. The other topic that's always discussed about is a little bit the question of what is quantum development? How can I code this at which level? And there are kind of two words. And I took this picture from a talk from Jura Sakotnik because it, I think, perfectly illustrates the point. So on one hand, you have something that looks like assembler code, and then you ask yourself, hey, if I work at this level, I probably take a million years until I get to something that looks like an app. And on the other hand, there are a lot of people who tell you, quantum computing will have a $100 billion industry, and you become rich very quickly. And then you sit in between and you ask yourself, but how? So that's what we looked into and built with the tools that exist in the stack, this showcase. And another question, and that's not a picture that I chose, but it's a little bit the question of like, how can we get along? So I'm a physicist. Didn't have an idea of software engineering when I joined Accenture. You helped me a lot, and other colleagues. So it's also a question of how can we actually do these projects end to end and realize something that's helpful. To state the point again, and I don't want to go too much into detail. I mean, there are a couple of stages on how far are these little proof of concepts, how far is the technology, and we typically, with clients, we meet questions like, what is it? The explanation you can get it on a physics level or on a higher level application side, and the question is a little bit like, how can I use it? How can I get my hands dirty, work with it? And then the question, like, what could actually be the value of it? And so there are a couple of ideas on quantum computing, how you could use it, for example, for paint job problems or maybe image classification. So these are like first ideas and proof of concepts that come up, and then there's a question: can it scale? Can it be efficient? And to be honest, currently the answer to that is kind of but impractical. Yeah, so we do have experiments where quantum computers solve a very theoretical problem in a way 1,000,000 times faster than even the fastest supercomputers and much more energy efficient. But there's not really kind of the one use case where it delivers value today. Now you could ask, how do I use them? So do I have to pay €1,000,000? The answer is no. Although these machines look nice and D-Wave is happy to provide one, or IBM, you can actually use them via the cloud. Yeah, here's one example. It's the symbol of Azure Quantum, the tool that we used. That gives you access to the quantum hardware and to classical high-performance computers together with algorithms, classical algorithms or quantum-inspired ones. And then you can essentially use this stack. Yeah? So there's the assembler level, where quantum information scientists work to build new algorithms. There's the programming language that is a little bit higher level. And then there's really algorithms and analytical data and problem models, which you can choose from libraries that already, let's say, integrate this and build on top applications within, at least get to something that you have a running algorithm within within a week or so. Yeah, the examples that are out there, or build something yourself. And actually, we are not the only ones doing this. So there's Goldman Sachs, JP Morgan, we really have dozens of people there that do the basic research. But there are a lot of other companies that try to make sure that they're to some level quantum ready, so that they don't have similar issues as you have with AI, that there are a few who are really good at it, and a lot that try it out, but can't really, let's say, leverage the results and results. So back to our solution and to our POC. What did we actually do? And Melissa already told you a little bit about this. Yeah? So we are looking at a quadratic optimization problem where you weight the returns that you get against the risk that is typically attached to the assets that you have. But we also include, and this is this little alpha over there, you include that you probably don't want to invest in Gazprom, for example, or you're actually not allowed to, probably. And you have other things that you weight a little bit higher than only getting the biggest bang for the buck, and maybe you want to improve the ecological footprint of your investment to a part. This alpha can be very low if you would like. So now the big challenge is that if you have a couple of assets and you have different sizes that you invest, then so large that there's no efficient way of like finding one solution. So typically you take sets of 50 assets and then you look at what's the best. So you somehow approximate it. Now, within, let's say, the Planck consortium and work that we did with KfW, we looked into algorithms that are not only theoretically working and need a lot of qubits, but we looked into algorithms that are actually hybrids between classical and quantum, so that use the quantum machine where it's best, and also provide circuits that you can actually run on a real quantum computer with only 20 qubits, for example. So there's all these nice gates and this classical optimizer that changes a little bit the gates until the resulting portfolio gives out a better performance value depending on your risk and sustainability preferences. And don't want to take too much time of demo that I really like. So there were a couple of interesting things that we actually saw. It's in a lot of ways. Most of these problems are sometimes very simple. Yeah? For example, if you say, I don't care about returns, I don't care about risk, but I want the most sustainable portfolio, then it's pretty easy that you tell me, hey, then just take the one with the highest value. Yeah, it's the same for being very risk averse or being very risk affine. Yeah, so there's a lot of ways where it's really easy and that you don't need a quantum computer. But actually, we had a couple of let's say instances where the classical solvers sometimes just let's say showed weird results, because there were very similar solutions also. And that was actually something where we found out that a couple of the solvers that are provided by Azure QIO, which is quantum-inspired computing, are performing similar or more reliably. And this is actually a rather nice result. Yeah, if you learn something about quantum computing and also find a new solver and problem configuration that might help to improve your little proof of concept robo advisor. And now I don't want to take more of the time and get back to the application.
Yes, so let's wrap this up in an application. So let's first look at the architecture of our Qupo app. We have basic front-end service which runs with React.js, and it's connected to a backend service which is written in Python, and it exposes basically two API endpoints. The tickers endpoint is just for the stocks to provide the symbols, and the models API endpoint is basically for value calculations and returning the results. And then we have, as you can see, the Yahoo Finance API. So we make fetch requests and for the stocks that we need, and we get back the stock prices that I showed you before. And these stock prices are actually also saved to the database. So if a portfolio in the future you want to include the stock again, it doesn't have to fetch and the stock prices from the Yahoo Finance API again. And then we get to the optimization backend, and in our optimization backend, basically all the magic happens. So we have the Azure client implemented, which connects to Azure Quantum, and also the IBM Cube, which is basically the optimization tool that provides libraries and makes fetch requests to the API, IBM API. So the process flow of our application is basically you ask our user to select a set of symbols, so the companies that you want to see in your portfolio, you select, and then in the next step you determine the weights. And I will also ask you that later on to do that for yourself. So we basically determine how risky you see yourself and how sustainable you see yourself. So to include this in the portfolio. And this we do by asking the user some questions, which you will also ask in the next slide. And then you can still adjust the symbols and the weights, and you choose the models. We have like 5 models to calculate with, and then you also set time frame, which basically takes the stock data from the time frame that you want to have included in your portfolio. And in the end, you calculate your portfolio, and either you adjust, for example, the weight, so you can compare the results with, or you start over the process again. And as already mentioned, I ask you to go to menti.com now and either scan this QR code or put in the code. And there are 2 questions that I want to ask you, but it's not about time, it's not about winning. I will just go through these 2 questions together, and you can just put for yourself how you see yourself. So the 2 questions that we answer is how risk-affine are you and how sustainable are you? Let's start with the first question.
Maybe one comment. Yeah. So this data will be only averaged, no personal information revealed, and also this is not financial advice.
Yeah, for sure not. So the risk weight. So to determine the risk weight, we consider the following situation. So we have lottery tickets at the kiosk, and there are 4 different types of tickets, and they all cost €1. So same price for each ticket, but they have varying rewards and varying chances to win. So which type of ticket would you choose? First, would you choose 100% chance of winning a prize of €1? So what you put in, you get back, basically. Or you take 80% chance of winning a prize of €1.25, or 50% chance of winning a prize of €2, 10% chance of winning a prize of €10, or 1% chance of winning a prize of €100. So please make your decisions. Okay.
A clear risk-averse tendency, I would say. Huh? Maybe a depiction of the current economic state, and everybody is a little bit more cautious.
Okay, I guess we have all. Okay. So yeah, I guess most of yours are more of the 10% chance of winning a prize of 10 euros. So it's quite risky, not completely risky, but quite risky. Okay. So let's get back to the next question. So for the next question, we determine the ESG weight, and we assume for that we assume a forward auction like on eBay, and we want to buy a portfolio with a good ESG rating. So keep in mind, only the bidder with the highest bid will win, and your overall portfolio budget is 10,000 euros. So the question is, by how much would you decrease your investment to bid at the auction? First, would you decrease your investment by €1 for additional 0.01% ESG value points? Or would you decrease your investment by €10 for additional 0.1% ESG value points? Or by €100 for additional 1% ESG value points? Or by €1,000 for additional 10% ESG value points?
Yeah, looks like the €1 and €100 betters are already out. People who would bet €1,000.
Yeah, also quite more sustainable. Okay, great. So this is we will put in this in the live demo your results, but for now it's just an example of this is not showing the right results of what you just put in. But it's just to explain you what you see here. Basically, that's our portfolio calculation. It's the result that we return to the user, and on the sides you can see all the companies that are included and all the algorithms that we calculated with. So you can see that the algorithms they spread out a bit, but are focusing mostly on ARG. And to be able to compare these results of the different algorithms with each other, we actually evaluate 4 values, and one is the performance of each result, which is basically the objective value of our portfolio. And the next one is the risk, of course. So for the risk, we take the portfolio variance, and which you can also see as 28 as an example. And then we have also the overall sustainability of the portfolio, which is basically calculated based on the weights of the stocks and the ESG values. And the expected return, which is based on the historical stock data that we use for our portfolio, depending on the time frame. And now we have a live demo, so to show you our application. Okay, this is our main page, so to say. And in a moment, it's just run it locally. And you can see here, you can choose a set of symbols, and we group them in indices, countries, or industries, so you can see which companies are included with just some symbols that we include, or you just can put in your symbols, search for them. Like Apple, for example. And then you can add them and move on. But for now, let's just choose probably the DAX, which is very quick. Yeah. And here you have the 2 questions that we also asked you before. So we had, I think, for the risk affinity, a chance of winning a prize of €10, and for the sustainability, I think it was €100 per %, right? Yeah, great. Okay, so we can move on, and then here you can see the symbols. In the moment, we just take 10 symbols in consideration, and the other ones are just all part of the DAX, of course, but we just take the first 10 symbols to calculate. Yeah, here you can also adjust the weights again, but we just leave it here for now. And here you can put in them, choose the models that you want to see in your portfolio. We just leave these 3, and maybe let's take the month, the September, as a base of calculation, and then we calculate, and you can see here I already calculated some. So here you can see our results and also here the performance basically. So you can compare how is the risk is quite the same actually. Also sustainability. You can also see that the it focus on bias stuff this time. It's also depending on the time frame, of course, which you can also see here and also adjust. And that's basically our portfolio. And then you can research the process or just compare it with each other with other results. Yeah. So I think that's basically. Thank you.
Thank you very much. And now we have time to take questions. Some direct question from the audience. Otherwise, I would directly answer the ones that are coming in over Slido. Or the one. Okay, so there's a question. What?
Yeah.
For the audience at home, the question is like, how does the access to the quantum computers in the cloud really work? And I mean, there are different, let's say, different access models. So there's for example IBM that have their own, let's say, their own platform, and you have to, let's say, create create an account, buy credits, like you do for EC2 instances or so, and then you essentially it's an API call. So they have a data center where a quantum computer sits, which has a classical computer interface, and then you send quantum programs, so quantum assembler code, to the computer. It sends back the results and measurements. Our little software piece translates the measurements of the quantum computer into a portfolio, and then we classically calculate the the performance.
A few seconds. It's depending on how complicated or how many data you send in. So if you choose more stocks, and that's why we choose just for now 10 symbols, because otherwise it takes quite some time to get the response. But and that's also why we cache the data basically, so to be able to provide more usability friendly application, because it does take some time, but it's manageable.
Heavily depends on what kind of subscription you have. And there's, I could talk longer about, there's now features. So actually the longest time it takes is sending the API request and then updating the circuit, sending it again. Yeah? So there are smarter ways to do this, which is called IBM runtime, or I think other providers are also preparing this. So yeah, but typically it's a couple of seconds, also because your quantum computer does have a very short coherence time. You can, after a while, only repeat the measurements. And then, I mean, it's a trade-off between accuracy and time. Yeah? You can also run it for a longer time and it will be a little bit more accurate. And then it can be minutes or hours. So there's also the question of what do you think about the announcement from Google in 2019? So what they showed is that at this time, the best known algorithm for a theoretical sampling problem, where you, let's say, create a distribution and try to recreate it with a classical computer. They took an algorithm that would have taken 1,000 years. So at that point, they were much faster than the fastest supercomputer. But a couple of years, I think half a year, a year later, somebody invented a new algorithm, and then they were faster again. Or they did it in minutes. What they did in years before. So I think the really interesting topic is that there's some very exciting race between classical and quantum algorithms, and we do hope that we can use the results of this also for some real applications. But there's still quite some work to do.
The next question is, when will we see real quantum computing applications? I guess the quantum computing applications don't exist like on a classical, like that you have on a classical computer. In the future, you can more see a quantum computer as always making a request to them than just having them at home, right? So we basically send an algorithm there and put the results in our application. So actually, this is quite a use case how it can be for real quantum computing computers, because then you will not have one at home and having an application running on them.
What other industries are benefiting most from quantum computing? Maybe that's so today none, yeah? But will benefit probably. I think a very good bet is simulation of molecules, as you can find in many publications. There are early simulations of small proteins that are in the area of cancer research or Alzheimer's. And IBM and others, they're really preparing their, let's say, quantum machines to build hybrid algorithms that are getting closer and closer to these, let's say, to the best classical algorithms. They're really making great progress. And I mean, if you believe their roadmaps and also the publications that they do on the, let's say, quality measures that they have, and then this could happen within this decade or in the beginning of the next. Then what are currently the biggest challenges for quantum computing and portfolio optimization? I think this is a very mathematical question, and there's actually much more detail to it than we presented it. So it's a question of you also include cardinality or so. Yeah, how big is do I want to get my portfolio at most? Because then it gets actually much more complicated. It's also a question of you use like continuous variables or discrete. So I wouldn't actually put out myself and tell the world what are the biggest challenges. This is probably something you have to ask the quants at JP Morgan. You can run it on a quantum computer, but I mean, for this demo purposes, we typically don't do it because either you pay a lot of subscription and the result is very similar, you don't see a difference. But you can, I mean, what we do is that we actually assess these quantum computers and compare. I mean, there are simulators that even include the imperfections of these computers. So in the development, use them to evaluate it. And then if you have developed, let's say, your algorithms and your approach, and you think that the results are good on the simulator, then you check if the quantum computer gives the same result. As long as classical computers can still compare to quantum computers.
So if there are no further questions, then thank you again. And if you have any questions afterwards, you can still approach us.
Thanks. Bye.